So in the past part of our video, we just have studied the electromechanical overcurrent relay. Right now, in this part, we will just study this numerical overcurrent relay. So here we will study how the electromechanical relay is different than the numerical relay. What are the features available for the numerical relay? Whether the features available in the numerical relay is better than or is more than the electromechanical relay. So all the things we will just study in this video. So let's see the aim of the experiment. So our aim of the experiment is study of operating characteristics of numerical overcurrent relay and plotting a graph between time versus fault current. In our earlier video, we have studied this part 1 of this video. In this part 2, we have to study numerical overcurrent relay. So, as like earlier, we need some apparatus to test this relay. So, let's see the apparatus. So, as you can see, same we need a power supply or current injection unit, same unit which we have used in the new electromechanical overcurrent relay, same to same exact same unit. And this top unit which earlier it was electromechanical overcurrent relay, right now it replaced with numerical overcurrent relay. And right now it is replaced with numerical overcurrent relay. And you can see and some connecting wires also we need. Also it's calculated 6 number of connecting wires we need to perform the experiment. So let's see details, because this power supply unit already we have studied in the part 1 of this video in details how this unit is designed, how to operate this unit. Right now we will study the relay unit, how this numerical relay unit, how the relay order is, etc. Let's see details. So the numerical overcurrent relay, the function of the electromechanical protection system are now being replaced by microprocessor-based digital protective relay. Because new modern technology is changing and new idea is coming. So this is the advanced level of relay which will give you more and more features compared to our old relay, or we can say electromechanical relay. This is not a mechanical relay, but due to this digital feature, it can give you more feature compared to electromechanical overcurrent relay, and we can call it as numerical relay. So what it does, as you know, it's a regular concept that in digital case, this relay converts voltage and current to digital form and process the resulting measurements using a microprocessor. That means voltage current is going inside, and inside the microprocessor it is deciding what to do or not to do. Then the digital relay can emulate functions of many discrete electromechanical relays in one device. That's Ruiz. Means this relay can have more feature than the electromechanical relay due to this digital. It can do more things. It can provide more information to the customer or to the user compared to electromechanical relay. Then it can simplify the protection design, because earlier, for example, using electromechanical relay might be using one relay for some purpose, another relay for some other purpose, one relay for some other purpose, like that. Your total panel, control panel will be bigger. But when we are replaced with numerical relay, lot of relay like 2, 3 or 4, 5 relay are replaced with one relay. So that means the protection system design is being simplified. And the numerical relay can also provide functions such as SCADA interface. As we know, all our substations, everything are interfaced with SCADA. So if you will use this numerical relay, only you can use this with the SCADA directly. If you have electromechanical relay, then in some indirect way you have to connect with SCADA, but this relay directly can communicate with the SCADA system, and it can monitoring of contact inputs and metering, waveform analysis, and other some things. Like as you know, some relays are there. You might be heard or not. Some distance relay which is used in the transmission line right now. Micom relay is generally called it as. That relay can be overcurrent relay, can be act as a arc fault relay, can be act as so many relays. This one relay can able to operate. One relay will protect whole transmission lines. Like that things is there. It can save all data, all fault, what are the fault waveform also it can give you. So modern technology, modern things, so modern idea is coming. Day by day also research is going on, so this protection system is going to be more and more reliable and more simplified. So this distance relay can, for example, store two set of protection parameters which allow the behavior of the relay to change during maintenance of attached equipment. This digital relay can also provide protection strategy impossible to synthesize with electromechanical relay. See, which is impossible in electromechanical relay, this digital relay can, and offer benefits in self-testing and communicating to supervisory control systems. And it can self-test whether I am good or not, or I am performing well or not. It can do its own test, and it can give information to SCADA that I am damaged. Like that, it also this modern type of numerical relay can provide that type of facility. So it is a microcontroller based. So basically it is a microcontroller based. So advanced relay also having DSP and also having so many embedded boards which can synthesize the current which can operate as per our record. But starting when the relay manufactured from electromechanical, when it transport to numerical, so initially it was used to microcontroller, but all DSP and all things are base is microcontroller. So it is a microcontroller based design for a wide range of drilled selectable trip time characteristics. Wide range of trip time characteristics. In our earlier electromechanical relay, we can have only 3-second characteristic. That is one type of sense. Only we can have inverse characteristic. So for instantaneous characteristic, we need another relay. For definite characteristic, we need another relay. Similarly, but here one relay can have multiple characteristics, and it can incorporate high set as standard feature. So high set is the most important part. Like as I told earlier, in electromechanical relay there is some thermal limit. Above thermal limit, relay may damage. But current we cannot predict how much it will be. It may be above the thermal rating of the relay. But you see, if you don't have any protection for that current, which will be more than the thermal rating of the relay, then obviously there will be damage on that. That means relay protecting the circuit, at the same time we have to use another relay to protect this relay. This type of things is there. But this type of things is not there in case of numerical relay, because it can have high set protection. That means instantaneous protection. That means if the current crosses the thermal limit of the relay, then relay acts as instant. So no characteristic it will see. It may damage my system, so it will act instantly. So that type of protection is there in case of numerical overcurrent relay. So it employs fundamental frequency extraction to ensure that it doesn't operate on spikes generated by switching of various loads. MC12A is designed for cross mounting. It is very compact in size, which results in saving of panel space. It draws out construction, makes installation and maintenance very easy. Cross mounting means horizontal mounting. Means like it can mount directly on the panel. Cross mounting. So overcurrent relay or arc fault relay model, as you know, we have to use MC12. This is the model number of the numerical relay which we will test in this experiment. So and this MC12A manufactured by L&T. is an electronic microprocessor-based non-directional single-phase overcurrent relay. It's a non-directional and a microprocessor-based relay. It is suitable for overcurrent protection scheme in low voltage, medium voltage, and high voltage power distribution system. MC12A is designed for flush mounting. It's very compact in size, which results in saving of panel space. Further construction makes installation and maintenance very easy. So see, what are the rating of the relay? This rating of MC12A, which we are going to test. Because whatever we are going to test, we should know what is the equipment, what are the ratings, we should see the specification or data sheet of the equipment. So these are the required information collected from the data sheet of this MC12A. And this MC12A manual and that or data sheet and that CDG11M data sheet will be provided separately with this video for your more information. So as you know, this MC12A is made by L&T and its current rating can be 1 ampere or 5 milliamp as like before, and its rated frequency is 50 Hz plus minus 2.5 Hz. Auxiliary power supply required. See, here auxiliary power supply required, but in the earlier case, no auxiliary power required. That is the advantage for electromechanical. But with having auxiliary power supply, it can give more feature than compared to electromechanical relay. So see, current setting. So earlier we can call for the any electromechanical relay, we name it as a clock setting for the pickup current. But in case of numerical relay, it is current setting or IS. Generally we pronounced as IS, and IHS we pronounced as high set current, means short circuit current, means whenever the current will cross the IHS, relay will act instantly. Whenever the current will cross IS, relay will act as per its characteristic set. So one of the three ranges is available, so out of which we can choose. You just select it. You can choose which range is needed. Accordingly, you can choose the current. And there is a time multiplying settings, and this can be 0.1 to 1.6 instead of 0.1. This TMS can be 0.1 to 1.6 instead of 0.1. And see what are the operating characteristics. The front panel programmable using push button. Whatever I told you that IES can be selectable and IEHS also can be selectable 2 to 16. So it can be 2, it can be 16, it can be in between. So that can be programmable from the front panel of the relay. That's why in front panel programming using a push button, or some switch is there, using dip switch is there. Using that switch you have to set the this IS, we have to set the IHS, we have to set the TMS, we have to set the characteristic. So from the front panel of the relay. So, and as we know, as I told you, I will tell you what are the characteristic is available. Different types of characteristic is available. That I will tell in this video. You see, here inverse type of characteristic, 4 type of characteristic are there in inverse type. To get more details of this type characteristic, you have to follow this standard IS 321 1987. If you follow this standard, or if you read this standard, there will be written about all the type of characteristic for the inverse. So what are the characteristic? First is normal inverse 3 second, normal inverse 1.3 second, very inverse, extreme inverse. So in our earlier case, that is the electromechanical overcurrent relay, as I told you, that is the 3 second characteristic. So that 3 second characteristic means that is the normal inverse 3 second. That means this 3 seconds signifies if you will apply 10 times the current setting, or if you will apply 10 times the clock setting current as a fault current, then this relay will trip at 3 seconds. Yes, this relay is designed to give you 3 seconds of trip time, but the actual trip time will depend on the TMS. If TMS will be 1, then the actual trip time will be 3 seconds. So these 3 seconds signifies that one. So that is normal inverse 3 second relay. And second one is normal inverse 1.3. Similarly, at 10 times of the current, what is the form factor? That is 1.3. That is normal inverse 1.3. Similarly, very inverse. Very inverse also has some constant, that is at 10 time what is the value. You can see by seeing the this one here. Very inverse means 1.5 second. That means 10 times of the current setting, it will trip at 1.5 second. 10 times of the current setting, it will trip at 0.8 second. That is nothing but the what? Extreme inverse characteristic. What is the extreme inverse characteristic? Similarly, definite time 1 second, definite time 10 second, definite time 100 second. So definite time 1 second, definite time 10 second, definite time 100 second. But this 100 second also can be manipulatable, that by the help of TMS. If TMS will be at 0.5, then the time will be 50 second. If TMS will be 0.1, time will be like 10 second. Depending on the value of TMS, we can set the definite time at 100 or below 100 or in between 100, in between 10, anything. But time should be fixed in case of definite time characteristic. So as you can see, this numerical relay can have this normal inverse or inverse characteristic, and can also have the definite time characteristic, and also can have the instantaneous characteristic by using these high set settings. And also this high set operating time is less than 50 micromillisecond for the input current less than 1.5 times of the IHS. That means when the current will be more than IHS, definitely it will trip instantly. But what is the time? Time is less than 50 microsecond. If the current is less than 1.5 times of the IHS or the high set current. If the current is more than 1.5 times of the IHS, this is okay, wrongly written, more than 1.5 times of the IHS, then it will trip at less than 35 milliseconds. You see the millisecond level it you are talking for. That is the instantaneous protection. Okay. Now as you can see in the earlier, this was our earlier relay which we have tested. But you can see here it is written overcurrent relay. That is the inverse take. And also another relay is there which is written Er.Bhanu relay inverse take. Similarly, another type of relay is there. They are written instantaneous overcurrent relay. So you can see three type of relay are there you have to use, but these three type of relay can be merged into one relay. This is nothing but MC12A. So now you see what is the difference between this Er.Bhanu and overcurrent relay. So in the, if you see from the specification or from the nameplate, nothing difference. Only difference is the clock settings. As you can see, only difference is the clock settings. So clock setting starting from 0.5 to 2. Here clock setting starting from 0.2 to 0.8. So these two differentiating the whether it can be used for Er.Bhanu relay or it can be used for the overcurrent relay. So as you know, overcurrent means this relay generally placed in phase of a supply, like RYB, like from source to load, some phase is there. From the R phase, this will be connected. Y phase, this will be connected. Another relay will be connected. That means in series with phase, this overcurrent relay will be connected. But this Er.Bhanu relay are generally connected between the neutral of the system to ground. It will see in a three-phase system, there will be 3 number of this type of relay and 1 number of this type of relay to protect the equipment. So that means any leakage current flowing from the transformer body to ground, or any equipment to ground, or any equipment neutral to ground, then this should be detected. That means this should be more sensitive. Er.Bhanu relay should be more sensitive than the overcurrent relay. I am repeating, Er.Bhanu relay is more sensitive, should have more sensitive than compared to overcurrent relay. As you can see, Er.Bhanu relay, that's why it is starting from 0.2. It can detect 0.2 ampere of current as a fault current, but this one can detect 0.5. Below 0.5, it will detect as a normal operating current, but below 5, this can be detected as a 0.2 current. As you can also expect, that why not these two relay are merged into one relay, and this PSM started from 0.2 to why not it was happened like that? Because due to the mechanical constraint, this PA's clock settings can be 7. So if clock setting can be 7, it will start from 2 to like 50 to 200%. How will come this 20 to 80%? So that's why the relay is separated. But in case of numerical relay, all these three things are combined into one. And another thing, here at 10 times of current we are getting 3, that's why this is normal inverse 3 characteristic. Here also 10 times we are getting 3, that means that is the normal inverse 3 characteristic. Similar fashion in this Alstom also manufacturing at 10 times 1.3, that is normal inverse 1.3 characteristic also we have manufacturing. So these different types of characteristic is useful for different types of load, different types of fault. So that is the separate chapter. Now you see, this is the front panel or the front image of this relay, and this is the relay unit or microprocessor-based or numerical overcurrent relay unit. So inside this unit, this relay is there, and this is the front panel of this relay. So from the front panel, as I told, the settings can be programmed from the front panel now. So these are the tip switch. These are the tip switch. Okay. So now you can see from the front panel how we can adjust the settings. So as you can say, first it is written IS. IS is nothing but 0.1 into R plus R summation of A. Summation of A means these are the A. So these are the A. So which switch is on, that value only you have to solve. If this all switch will be off, then sum of A will be 0. If all switch will be on, then sum of A will be sum of 0.16, all this like 0.16, 0.2 and then 0.3. 0.2 and 0.3. So total sum of A will be, maximum will be 0.3 and minimum will be 0. As you can see, if you apply this value 0, now what will happen? 0.1 into R into IN. IN is nothing but the normal operating current. IN is nothing but the normal operating current. And IN means that is the rating of the relay. IN also signifies current rating. Like in earlier case, city secondary is nothing but the current rating. Similarly, here IN is nothing but the current rating of the relay. And here in this case, which relay we are using, that is IN equal to 1 ampere, because current rating of the relay is 1 ampere. So we have to apply 1 ampere here. Now R, what is the value of R? So this R value can be decided by setting the current selection range. That means R is nothing but the range. What are the range you have selected? Corresponding to the range, R will be decided. So as you can see here, so these are the range selection switches. These are some inside the unit. Deep switch is there, and the position of this deep switch 1, 2, 3, 4 switch will decide the current selection range. So if the position is on, off, like this, it will suit, then it will be 10 to 40% current selection range. So if 10 to 40% means our R will become 1. So 10 to 40% means our R means that which used in the formula of IS, R will be 1. Similarly here R will be 2, similarly here R will be 5. So to get a different value of current selection range, we have to choose this set of settings. And let's come here. So here R you can select using this one, and this switch is inside this box. As you can see, this switch is inside this. This switch SW1 is this one, SW2 is this one. So use this switch and arrange according to the configuration given and select the current selection range. And this is nothing but switch 2, and arrange this configuration and select the characteristic type. According to different position of this switch, the characteristic will be decided. We can set the characteristic using this switch. So if all switch will be off, like it's showing this one is off and offside is on, so all are off, so that means that is normal inverse 1.3. Right now it is looking like that. So when we will perform the experiment, that time we will set and we will see what is the characteristic. And as you can see, R is nothing but, let R will assume as 1, minimum R can be 1, maximum R can be 5. So 0.1 can be the minimum IS. So as I told in the electromechanical case, that to the relay, if it is used to operate, or it can be used to operate as a hard fault if it can detect less amount of current as a fault current. Means if relay will be more sensitive, then only it can be used for the fault relay. As we know, the IS is 0.1, so that means this relay can be used for the fault relay. And similarly, maximum how much IS we can set, that R can be 5 and summation of A can be 0.3. So how much will be 5 into 0.3? So 5 into 0.3, it will be how much? Let's see. So 5 into 0.3 will be 1.5 and 5 into 0.1 it is 0.5. So 0.5 plus 1.5, that is 2. So maximum IS can be 2. That means this is most. The clock setting or the current setting starting from 0.1 to 2 ampere. That means this relay is capable to handle at fault current and also capable to handle overcurrent in a phase. So in this way you can set the IS and also you can calculate the value of IS using the what are the position of the switch, what are the current selection range, and what are the position of the switch, what is the value of summation of A. You can calculate the value of IS. Now coming to IHS. IHS is nothing what I told you, that is the high set current. High set current means the instantaneous current limit. So this high set current also having some formula that is written here, 2 plus sum of B into IS. That means it is some times of IS. If sum of B, let it will be 0 and this will be 2 times of IS. That means minimum IHS can be 2 times of the current setting. Let current setting is 1 ampere, then this can be 2 ampere. That means if the fault current will cross 1 ampere, relay will trip according to the characteristic set. Here the characteristic can be set using this S2. Whatever the characteristic set, according to the characteristic, relay will operate if the current will cross IS. But if the current will cross IHS, then it will not bother about whatever the characteristic you have set. It will trip instantly. So this is the relay internal protection, or this is the instantaneous relay. That means this relay overcurrent fault as well as instantaneous relay can. So we can able to use this relay. And how to set this sum of B nothing but this switch position. So there you can see 8, 4, 2 and enable is there. That means we can enable the IHS and we can disable the IHS as per our requirement. So if this switch is on, means 8 is available, or as you can see from the image, 8 is on, this is off, this is on, this is on. That means IHS is enabled, last switch on means IHS is enabled, and 2 plus 8 is there. 2 plus 8 is there. That means 10. So sum of B is 10. So sum of B is 10 plus 2, 12 times of the IS. That means if you are applying 12 times of the IS, this will trip instantly. The maximum IHS will be how much? Maximum IHS will be 8 plus 2, 10 plus 4, 14. So 14 plus 2, how much? 16. So maximum IHS can be 16. Minimum can be 2. 2 times of IS, maximum can be 16 times of IHS. As I told you, here it is written IHS 2 IS to 16 IS. And also option of disable or enable. Then comes to T. This T is nothing but the time setting multiplier. This T is nothing but the time setting multiplier. As like earlier there was this is the knob. This you have to rotate to set the time setting multiplier. But here you have to choose the tip switch. So here 0.1 plus sum of T. So sum of T can be maximum of 0.9. It will 0.8 plus 0.4. So it will be 0.1 plus 0.8, 0.8, 0.2. It will be 1.0 plus 1.1, 0.5. So 1.5. So 1.6. That means maximum T can be 1.6. Let K as right now K, let as much K1. So minimum T can be here right now 0.1, and without K or K at 1, T will be 1.6. So that's what it is written. That 0.1 to 1.6 instead of 0.1. So that is the TSM. But what is K? K is nothing but the constant, and this constant is decided by the characteristic set. So as you can see, for different value of K, so the value of K is 1 for normal inverse 1.3, and for definite time 1 second K is 1, for definite time 10 second K is 10, and for definite time 100 second K is 100. That means whatever we will get, that is time setting multiplier, that is starting from 0.1 to can maximum 1.6, and that can be multiplied into the 1, 10 and 100 to get wide range of time setting multipliers. So that means time setting multiplier also can be more than 1. Here in case of electromechanical overcurrent, numerical overcurrent relay. But in case of electromechanical overcurrent relay, that is the mechanical constant, that TMS cannot be more than 1. But here in case TMS can be more than 1, also can be less than 1. So the wide range of time setting multiplier, wide range of trip time characteristic, and wide range of current setting, and as well as the high set. These are the extra advantage of the MC12A relay or the numerical relay. So let's go some more details. So this is the switch which will be. So if you see the panel, relay is there inside of the panel, but else is there only the connection from the relay output to this terminal. Because if you see the relay terminals, you may confuse, but to do experiment, to make your experiment little bit easy, what is it did, this company, like all the terminals he displayed here. So 11, 12, 7, 8, 9, 7, 8, 6, like that terminal. So let's see what are the terminals. Let me zoom it. So as you can see here, is 11 and 12. As you can see in the diagram also it is mentioned 1, 2, 3, 10, 11, 12, and this side 5, 6, all terminals are there. So as you can see the auxiliary supply here, it is showing phase neutral. Auxiliary supply you have to give, that is to here also it will be 95 to 240 volt. That means AC or DC. Here we can give as per our current injector unit. We will give 230 volt AC, where at terminal 3 phase and terminal 2 neutral, and also we have to ground the relay, and we have to connect a terminal 1 to ground. Like this 1 will be grounded, this will be 2, this will be connected to the neutral of the auxiliary supply, 3 will be connected to the phase of the auxiliary supply. Similarly 10, 11 and 12. So 10 is not connected. So 10 terminal also not available here. So 11 and 12 is the output from the city. That means the current will be inserted at this 11 and 12 terminal. That means current injection unit, whatever the current injection unit output will come to 11 and 12 as per this diagram. Because if you see this diagram, you don't need to remember the connection diagram. Only by seeing the terminals only we can connect the setup and do the experiment. So this 11 and 12 will be connected from the current injection unit, and as you can see current is coming, and a converter is there and microprocessor is there. It is deciding, and according to the its range or something, then it is giving signal to the trip command, and according to the output is coming. So in the output what I will see there 5, 4, 6. Here you can see this switch is connected with 5 terminal is connected with 4. That means 5 and 4 you can use as a normally closed terminal. That means wherever the circuit breaker require NC terminal to trip, we have to give 5 and 4 to the NC terminal of the circuit breaker, or 4 and 6 to the NO terminal. No, 5 and 6 to the NO terminal of the circuit breaker. That means 5 and 6 will be NO terminal, 5 and 4 will be NC terminal. Similarly, here 8 and 9, 7 also same concept. 8 and 9 will be NC terminal, 8 and 7 will be NO terminal, 5 and 6 will be NO terminal, 5 and 4 will be NC terminal, and this 1, 2, 3 auxiliary power supply. So this from this one or from this one any terminal you have to get this one to the relay and to the current injection unit or to the circuit breaker, and from the current injection unit current should be come here, and auxiliary power supply also from the current injection unit should come here. So in this way the circuit will be connected. So you see next, this is the diagram as I showed earlier. So next we can also see by seeing the model number. What is the model number here? We will see. Okay. Here, what is the model number? Okay. So here it is not written, but in the manual it is written. So according to the model number, that is MC12A or whatever is written. So MC12A is the relay, and this A signifies which power supply. We are having 24 to 110 volt or 110 to 240 volt. So we are having this B 240 110 to 240 volt SPC power supply, and 1 is nothing but secondary. It may be 5. Model number 5 means it can be 5 ampere current relay, and 1 means 1 ampere relay. Similarly, we can find the numbers. So like that, model number of the relay manufactured by LMP is categorized. This also understood, and here this all different type of characteristic you can set using the dip switch number 2, which is available where? Here. It is available here. This is the dip switch number 2, dip switch number 1. So now come to power supply. So as you know, this power supply specification already we have discussed in the part 1 of this video. So we will not discuss anymore. So directly we can go to the connection diagram. So we will go to the experiment table and we will perform the experiment. We will connect the circuit and we will perform the experiment and we will take the observations. So if you will see the observation table here, so we need TSM, IS, fault current, trip time is second. So these two trip time is this may be required for the calculation of trip time using the electromechanical relay, but here directly we note down the trip time, because in our numerical overcurrent relay we cannot predict the trip time by seeing the relay. We can predict the trip time by seeing the characteristic, and by seeing the characteristic equation we can calculate the trip time, but by seeing the relay we cannot calculate the trip time. It is a numerical overcurrent relay, which has happened in case of electromechanical overcurrent relay. So we need TSM. So we need TSM means we just have to see what is the value of TSM right now. So as already I have explained you that this one, this TSM, this T is nothing but the TSM of the relay. So right now it is 0.2. As you can see here, this is the summation of T 0.1 K and T. This T signifies your time setting multiplier, and here 0.2 in case of summation of T, as you can see 0.2 and all are off. So you can see summation of T is 0.2 and your 0.1, 0.3. So time setting multiplier is 0.3. We can change this one to, let we need 1 as a TSM. So we can change this to 0.1. So 0.8 we need. So let change this knob. So as you can see right now the setting is 0.8 plus 0.2 is nothing but summation of T, and then 0.1 is nothing but 0.1 plus 0.9, 1.0. So T is nothing but your time setting multiplier is 1. That's subject to which characteristic we have set. As you can see here, this for setting the characteristic you have to see here switch 2 you have to see here to set the characteristics. The switch to position like off, that is normal inverse 120. Let's see what is the switch to position. As you can say, this is 1, 2, 3, 4 and this is 1, So 2, 3, 4. Let we will make into normal inverse 1.3. So right now you can see this is all are off. Off side is on. The bottom side is off. So all are off. So that means this is normal inverse 1.3. So for normal inverse 1.3, our K value here in the case of PSM, that is 1. So time shifting multiplier is nothing but 1 right now. Next come to IS. So let me calculate here. So T, what we observe, T is nothing but K to 0.1 plus summation of T. Summation of T we got 0.9. So and K is becoming 1 because we have selected normal. K is 1 because we have selected normal inverse 1.3 characteristic. So this will be 1. So your PSM is nothing but 1. You can write PSM that equals to 1. Right now we will set for the current setting. As you can see, the current setting formula IS is nothing but from the relay you will see. From the relay you will see that is 0.1 R plus summation of A to IN. So that is 0.1 R plus R into summation of A to IN. See the formula for this one IS. So what is the value of R? Let's see. The value of R here can be calculated by seeing this which current selection range we have selected. So as you can see here, we have selected off, on, off. So that means off, on, off. So that is 10 to 40% current selection range you have selected. That means this IS can be minimum value 0.1 and maximum value can be 0.4. So right now R value for this one is 1. So let's apply the value of R, and what is the sum of A will here already it is there. This is 0.02 is turned on and 0.08 is turned on. So this is 0.08 plus 0.02, that is 0.1. So what will be the value of R? So here 0.1 into R value we have seen that it is 1 plus 1 into 0.1. So overall in this IN is for the normal operating current, that is relay rating we also can say. So into 1. So this is becoming 0.2. So 0.2 is our IS. So IS is 0.2. And fault current, how much fault current will give? So generally more than 0.2 you just have to give. So you just have to give 0.35, next 0.45, next 0.55, 0.65, 0.75, 0.85, 0.95, 0.1, then we can opt for some higher current at 1.5 and 1.8. Like that we have to give. So this is the set we have to, this is the value we have to set before performing the experiment, so that directly we will apply this amount of current and we will note down the setting. That is our algorithm. So now you will see what is the procedure to perform this. To get this result, what is the procedure? You just have to see. Right now, if you will see the procedure, then what we are looking in the procedure is first we have to connect the circuit as per the connection diagram. So as you can see, already we have connected the circuit here. That is ready. Next, ensure the time interval meter selection switch to pin position, as already we have did this time interval position should be in pin position. Then ensure protection timer should be bypass. So here protection timer switch, this is in bypass mode. Then bring dimmer to 0. So this is the dimmer. We have to rotate anti-clockwise to make this dimmer to 0. Then calculate the current setting IS and TSN by using appropriate formula. So which also we have calculated and we have noted in the observation table. Then put on the mains using mains on rocker switch. So this is the mains rocker switch that we have to switch on. Then select the current using current selection switch. So here, if you see the observation table, so from here to up to here we can select current selection switch position as 1, and from here to here we can select current selection position to be 2 as per the current rating. So depending on how much current we are going to apply, depending on that we have to select the position of the current selection switch. Then after that, so right now we will start from 0.35. So we just have to see the position of the current selection switch to be 1. So here it is in position is at 1, and here this position is that is a rotary switch, that position is also 1. So as you can see, the rotary switch position is 1. Then push stage start button. So push stage start button. So stage start button is pushed, and then what we have to do is, here is the procedure, adjust the dimmer position for a particular value of fault current. So for fault current 0.35, we just have to see 0.35 here, that because position of the current selection switch at position number 1, so the ratio is 1:1, so we just have to see 0.35 here. So we have to increase this one, and we just have to go for the 0.35. So 0.346, 0.35. So 0.35 is the current. Now we will allow the current. But you have to do like this. And you have to do the rotary switch position to 2. And here you can see this indication is going, means relay is going to trip. So we have seen that this relay given 7.00 seconds as the trip time for this amount of current. Now we will same process as like electromechanical. We will reset the power supply unit, and then we have to change the position of the rocker switch to position 1, and then we have to again turn on the circuit breaker or test start button, and then right now we just have to apply 0.45. So 0.45. So 0.45, then we will apply the current. So it gave 4.00 second as the current trip time. This is 4.00 second as the trip time for 0.35, sorry 0.45 current. So next, similarly, test stop and position to be 1, and again test start, and we just apply for 0.55. So then we have to turn on the S2. So we got 3.2 seconds. So this is 3.2 seconds. Next, 0.65. Turn off, change the switch, and here every time we just have to make this dimmer to be 0. But when you are in the one position, like current selection switch position at position 1 or any position, then in that position you don't need to change this to 0. When you are changing the position specifically from position 1 to position 2 or position 3 of the current selection switch, so before turning the first observation, after changing the switch, you have to make this variable to be 0. So that is the pre-requirement. But here, if you do, it's okay. It will not do also. It's not be a problem for the relay. So we have observed 0.55. Now it will be 0.65. So turn on and we just have to apply 0.65. Okay, 65. We observe 2.7 seconds. So this is 2.7 seconds. So our next observation is 0.75. So test reset. This to be 1 and 0.75. Then test start and 0.75. Okay, so again like this. 2.5 seconds. So you observe that 2.5 seconds. Next 0.85. 0.85. Now we will apply for the 0.85. As you can see 0.85. 2.2 seconds. So 2.2 seconds. Similarly, we can go for the 0.95. So we change this position, and here external and 0.95. So 2.14. So we are getting 2.14 seconds. Similarly, right now we can apply 1 ampere because this maximum at this one position of the current selection switch you can apply 1 ampere. So this is our last observation in this position, means in position of the current selection switch at 1. So change this to 1. This is 1. Then test reset. Then on and we will make 2.1. A bit less. So 2.0. So next is 1.5. These two observations we cannot take in this current selection range selection switch position 1. So right now we have to change the range selection switch position to be 2. So as you can see here, I have changed to 2 here. As I already shown you the image of this switch, so by looking at the image you can also predict. So there that side this one is nothing but the current selection switch position. This one nothing but the current selection switch, and this is nothing but the rotary switch. This rotary switch helps to means this allows the current to the relay. This is the switch which bypasses the current through it and not allowing current to the relay when you are setting the relay. That means when you will test some relay, so first you have to set its parameter, means whatever the required input for the relay. Then after setting the parameter, then you have to apply suddenly the parameter. To facilitate this type of facility, that type of switch is there. So in our next experiment also, in our voltage experiment, we will see how that type of things is being realized. Like when you set, there should not be any voltage or parameter available on the relay, and after setting the relay, then the parameter will go to the relay, or like parameter may be current for the overcurrent relay, maybe voltage for the over voltage or under voltage relay, and for which type of relay the input is the parameter for the relay. So our next observation is 1.5. So for 1.5 at question number 2, we just have to see 0.75 here. Just have to see 0.75 here. So right now I told you that I changed the current selection switch position 1 to 2. So again we have to make this dimmer to be 0. This is required because at this position earlier, at that current 2, current may be more than 1. So it may damage our circuit. That's why this is the precaution that this should be 0, but specifically when you are changing the position, after that this will be 0. So right now I will turn on this one, and for 1.5 how much we have to see? 0.75. 0.75. Reset 0.75. So we just have to see 0.75, 0.65, 0.75. So little bit less. Okay. So 0.75 applied, we got 1.6 second as the tripling. For 1.5 ampere current, we are getting 1.6 second. Similarly, for 1.8 ampere of current, we have to see how much? 1.8 ampere of current, we just have to see 1.8 by 2, so that is 0.8. So we just have to see 0.8 here. So already we have at position 0.75, directly we can reset, we can change the position to 1 and we can start this, and we can 0.8 you have applied. Now it should go to trip when we will change the position of rotary switch to be 2. So this is going to trip, so 1.5 second. So 1.5 second. So this is the observation we just have taken in this experiment, and after that we just have to plot the graph between trip time and process fault current, and we will analyze that what we concluded after doing this experiment.
So the conclusion of this experiment, what we did in part 1 and part 2, what we can conclude that this numerical relay is having more facility than electromechanical relay. It can have combinedly can operate 3 electromechanical or 4 electromechanical or multi electromechanical as one relay. It can replace the number of relay to 1. So the circuit will be a little bit easy, and it reduces the complexity of the substation design, but it does require the auxiliary power supply, which is mainly the, you can say, if auxiliary power supply is reliable, then this numerical relay will be mostly reliable. For right now, as you know, auxiliary power supply also are being more reliable. If you are giving from the DC power supply like from the battery and all, then it is becoming more reliable. But instead, if it doesn't have that, then the electromechanical relay will be more reliable in that case. So this is the conclusion of the experiment.